Okay, in this video, we are going to calculate the directional derivative in the direction of v, a vector, at a given point. And we are continuing with an assignment from my Calc CD class. So let's keep going. So question 21, the function is f of xy, which is x squared plus y squared. The vector is going to be 4, 3, and we are looking for the directional derivative at 1, 2. All right, so to find a directional derivative, the notation is d and then the vector and then f. But the key here is that the vector has to be a unit vector, and we weren't given a unit vector, so we're going to have to find that. But the directional derivative is just the dot product of the gradient of the function with the unit vector. So if we know the gradient and we know the unit vector, we basically can do the problem right away. So we are going to need the gradient. So the gradient is just partial x, partial y. So partial x of x squared plus y squared is 2x. Partial y is 2y. So our gradient is 2x comma 2y. We also need a unit vector. So let's divide this by its magnitude. The magnitude is 5. That's a Pythagorean triple, 3, 4, 5. So we're going to do this dot product, and then we are going to evaluate at 1, 2. So our directional derivative at 1, 2 is going to be, I need to take x equals 1, y equals 2, and sub into the gradient. So that's going to give me 2 times 1 and 2 times 2, so 2, 4. And our unit vector we found, so 4 fifths, 3 fifths. So the dot product is like first times first plus second times second. So it's going to be 2 times 4 fifths, which is 8 fifths, and 4 times 3 fifths, which is 12 fifths. So that's 20 fifths, which is 4. That is the value of the directional derivative. Let's look at the next one. All right, so this is 23. F of xy is x squared y cubed, and then our vector is I plus j, which is really just 1, 1 in component form. And then we want to evaluate the directional derivative at 1/6 comma 3. All right, so same set of stuff that we're going to need. Our directional derivative is the gradient dotted with the unit vector. I write that for every problem so that I'm very focused on what I'm doing. I now need to find the gradient, which is going to be partial x comma partial y. So partial x is 2xy cubed, and partial y is 3y squared times x squared, or 3x squared y squared. So you treat x squared as a constant, right? I don't know why I'm struggling with this. X squared y cubed, the derivative with respect to y. X squared is a constant, the derivative of y cubed is 3y squared, 3x squared y squared. I over-explained that. You're welcome. All right, now I need to turn the vector into a unit vector. The vector is 1, 1, which has a magnitude of square root of 2. So I'm going to divide by square root of 2. So our unit vector will be 1 over root 2, comma 1 over root 2. I'm not going to rationalize that because I don't think it really helps. So we need to actually do the dot product, but we're going to evaluate at 1/6 comma 3. So when you plug 1/6 3 into this thing, into 2xy cubed, you're going to get 2 times 1/6 is 1/3 times 3 cubed. So 1/3 of 3 cubed is 3 squared, so you get 9. Then when you plug into 3x squared y squared, you get 3 over 36 is 1/12, and then times 9, so 9 over 12 is 3 over 4. So I'm just plugging in there. I need to dot product with the unit vector. And then I don't know the best way to write this. So I'm going to get 9 over root 2, and then 3 over 4 root 2. So I'm going to get a common denominator, which will be 4 root 2. So you get, the first fraction needs 4 over 4. So you get 36 plus 3 is 39 over 4 root 2. You could rationalize that and get 39 root 2 over 8, if that's better. I'm not sure which is the best way to write that. Let's take a look at the next problem. So f of xy is arctan of xy. Our vector is 1, 1 again, and we're going to evaluate the directional derivative at 3, 4. So same stuff, right? Directional derivative is the dot product of the gradient with the unit vector. We need to find the gradient, and we need to find the unit vector. These are really just practice problems in finding gradients, I think. It's like you're practicing finding your partial derivatives. So the gradient is partial x, partial y. Partial x. So the derivative of arctan is 1 over 1 plus u squared times the derivative of u. If we're taking the derivative with respect to x, it's going to be 1 over 1 plus xy squared times the derivative of xy with respect to x, which is y. So we'll have y over 1 plus the quantity xy squared. Kind of by symmetry, you know that that partial y is just going to be x over 1 plus the quantity xy squared. You get a lot of symmetry with these partial derivatives, but we're still doing 1 over 1 plus u squared times the derivative of u. The derivative of xy with respect to y is x, so we're going to have x over 1 plus xy squared. We need our unit vector as well. It's again going to be 1 over root 2, comma 1 over root 2, because the magnitude of 1, 1 is root 2. So to get a unit vector, you take the vector and divide it by its magnitude. All right, and then we have to evaluate this thing at 3, 4. So nothing amazing is going to happen here. Y is equal to 4, so we'll get 4 over 1 plus 3 times 4 is 12. 12 squared is 144. 144 plus 1 is 145. So the denominator is 145. So we have 4 over 145, and then we'll have 3 over 145. Okay, so that's what we get there. We're going to dot that with our unit vector, which is going to give us the sort of ugly answer of 4 over 145 root 2 plus 3 over 145 root 2 is 7 over 145 root 2. It's not going to look better if I rationalize that, so I'm leaving it. All right, number 27 is next. Did a lot of odds, and that's okay. F of xy is the natural log of x squared plus y squared. And our vector is 3i minus 2j, which I'm going to think of as just 3, negative 2. And we're going to evaluate this at 1, 0. Same game plan. Write down your directional derivative. You got to find your partial derivatives because you need the gradient. So it's going to be 1 over x squared plus y squared times 2x when we're doing partial x, comma, 1 over x squared plus y squared times 2y when we're doing partial y. So 2y over x squared plus y squared. Unit vector, the magnitude of 3, negative 2 is the square root of 3 squared plus 2 squared, the square root of 13. So we get, I'm going to write it in component form, 3 over root 13, comma, negative 2 over root 13. All right, so we got to think as we sub in here, but we're subbing in 1, 0, so it's not as bad as it might seem because the 0 for y is going to make things really nice. So you get 2 over 1 plus 0. You get 2, and then you get y is 0, so you just get 0 for partial y. And this, now y is not contributing anything here to this to this directional derivative. So we're really just going to end up with 6 over root 13. Good problem. Again, we're just practicing doing partial derivatives. We got one more of these, so let's do it. Got g of x, y, z, this is number 29, is x e to the negative yz. Our vector is 1, 1, 1, so it's a 3-dimensional vector, and we're going to evaluate this at 1, 2, 0. The plus side of this is that nothing changes. Our directional derivative is still going to be the gradient dotted with our unit vector. So I'm going to write that down. I changed from f to g, though, because it's named g. We need to find our partial derivatives. All right, partial x. You have x e to the negative yz is a constant, so the derivative of x is 1. So you have 1 times that constant. You just get e to the negative yz. Partial y. So you have e to the negative yz. The derivative of that with respect to y is negative z e to the negative yz, and then there's an x. So we're going to get negative x z e to the negative yz. And then partial z, kind of by symmetry, the x is just a constant multiple. The derivative of e to the negative yz, where z is the variable, is negative y e to the negative yz. So we're going to have negative x y e to the negative yz. Okay, we also need a unit vector. The norm, or the magnitude of 1, 1, 1, is the square root of 1 squared plus 1 squared plus 1 squared. So the square root of 3. Divide by that to get a unit vector. So we have 1 over root 3, 1 over root 3, 1 over root 3. Okay, so we have all this. And now we're going to do it. We're going to evaluate it at 1, 2, 0. So if you plug in, if z is 0, it makes all the e to the negative yz's e to the 0. So those are just 1. They basically don't exist. So first we're going to get 1. Then you get x times z is 0, so 0. And then negative x times y is negative 2, times 1 is negative 2. Okay, we got to dot that with our unit vector. And so that's going to be 1 over root 3 minus 2 over root 3. We get negative 1 over root 3 as our answer there. Not bad. All right, I'm going to cut this one here, and then there are 2 more problems in this assignment that I'm going to come back in the next video and do. Hope this was helpful. Good luck.